Okay, so in this first one, we're going to start with the tangent equation. All right, do you guys see any sort of vertical stretch happening? Yeah, what is it? 2, absolutely. Because that distance from the 2 points, it's not just over 1, up 1. You went up 2 to get to that 0, 3. So we know we have a 2 out in front. We have a stretch. We said we're going to do tangent first. I'm going to do the b value last because that's the part you have to think the most about. So then we'll have some sort of phase shift and some sort of other shift. So as far as the shifting, tangent normally has a point that goes through 0, 0, right? Like that's sort of the center of your tangent curve. That point is now up here. So how do you get from the first smiley face to the second smiley face? Like where did you go? Up, down, left, right, what happened? Left by pi over 6 and up 1, good. So since it's left by pi over 6, I'm going to say plus pi over 6. And then I'm going to say plus 1 at the end because we went up 1. Are you guys okay with those, like, 3 pieces of it? Okay, the period part. When you're doing tangent and cotangent, asymptote to asymptote is a whole period, like a whole cycle of the graph. So I know this first asymptote here on the right side, we know that's at pi over 6. Okay, that's been labeled for us. We just need to figure out, okay, where is this other asymptote? So I'm just going to like count my way over. This is negative pi over 6. Negative 2 pi over 6. I know that reduces. Negative 3 pi over 6. So how far is it between negative 3 pi over 6 and pi over 6? 4 pi over 6. That's the period of this graph. It is 4 pi over 6. Now we can reduce that to 2 pi over 3. I don't need just the period, though. I need the b values. Do you guys remember that little fraction we would set it equal to? What is it with tangent and cotangent? Yes, pi over b. So I'm going to set that equal to pi over b. And then just algebra here, I'm going to solve. I'll cross multiply, so I get 2 pi b equals 3 pi. So b, do you guys see it, is just 3/2. So that's what goes in the b spot of the equation. And there is your first equation. Okay. Anybody get it? Yes, okay, a few, good. Does it make sense now? Like, do you see all the pieces? Okay, so let's try to turn it into cotangent. Only a couple of things are going to change for turning it into cotangent. First, cotangent goes like the opposite direction, right? Like the curve goes the opposite way. So what do I know? I need to have a negative. Yeah, so we're going to start with negative 2 cotangent. The stretch is still the same. The period is still the same, so that b value will not change. X, and then I'm going to leave a little space there because the phase shift is different, but the plus 1 at the end is still the same. All right, if you think about cotangent, what normally happens on the y-axis for cotangent? Asymptote. Yeah, there's normally an asymptote there. So to figure out the sideways, the phase shift for cotangent, just look at an asymptote and where it moved to, that's your shift. So you could either go left by the 3 pi over 6 or just right by pi over 6. So I'm going to say x minus pi over 6. And you're done. So with these, once you've written one equation, you have almost everything you need to write the other equation. Okay? A lot of the pieces will not change. There are other ways you could write that. With your shift, you know, different shifts could happen, but anybody questions on the first one? Okay. Okay, let me give you another minute here to keep working on this, and I'll give you a little nudge. Let's see. I'll draw in the cosine-ish graph for you and see if that helps you try to write the equation there, okay? Is the what? I'm sorry. This one? You have to figure out where it is. It's on the midline of cosine, though, if that helps you. Check in with someone around you. Do you have the same thing? Some of the same pieces, at least? All right, guys, let's take a look and see how you're doing getting there. So I drew in like a little section of the cosine graph because to me this looks more like cosine than sine. Does everybody agree with that? Like we've got the maximum on the y-axis. Okay, so I'm going to write a secant equation first. I sort of sketched in the midline there. Remember that's halfway between like the bottom and the top of this. So if we're going from -1 up to 4, how far is that? 5. What's half of 5? 5 halves. Yep. So 2.5. So just 2.5 away from either side. That's where your midline is going to be. What else does that 2.5 or 5 halves represent? What is it? Yes, that leading coefficient, that stretch that's going to happen. So you can write 5 halves. You can write 2.5. I do not care. All right. Again, we'll do the b value last. There's actually no phase shift, no sideways shift if we're looking at it as cosine, because it starts with the maximum on the y-axis, and that's what cosine always does. But let's think about our vertical shift. Remember, the vertical shift is the midline. So where is our midline? Sorry guys, what? We're very quiet. 3/2, yeah, so say plus 3/2 or plus 1.5 at the end, either way. So we have the vertical shift taken care of. Again, it's always the midline. Now, as far as the period for this one goes, again, look at cosine to figure this out. Do you guys see how from 0 to 5, how that looks like half of the cosine graph? Do we see that? I'd have to finish up here to be the entire cosine, like one cycle of the cosine graph. So if half of it shows up at 5, what is the full period of the graph? 10. Okay, 10 is not what I need in my equation, though. I have to solve for the b value. So what do I set 10 equal to? For tangent and cotangent, it was it was pi over b. What is it for? Yeah, 2 pi over b. And then you're just algebraically solving. What do we get for our b value at the end? Pi over 5, guys? Okay. Multiply by b, divide by 10. That's what we're doing there. So I can just plug that in here. I'll have pi over 5, and I can just say times x, because I don't have a phase shift if I'm doing secant. That is your first equation. Let's stop here for a second. Questions on any of those values in that first equation, the secant equation? Okay. I'll give you a minute here. All right, let's try to write cosecant. So normally sine would go through 0, 0, right? Like that's what the sine curve does. Obviously, it's been stretched. It gets shifted up to move here. What else is wrong with the way this curve looks as far as like regular sine? Do we see anything that's weird?
It goes down.
Yeah, it goes down first. That's not what sine normally does. So one way you can write this is with a negative in front because it's going the opposite direction that sine would normally go. So I'm going to say negative, and then it is still the 2.5 out in front, or 5 halves. That does not change. The b value of pi over 5 will not change. But let's think about our shift here. The plus 1.5 won't change either, but the phase shift definitely does. So again, if you're thinking that's where sine normally starts, and it has to end up over here. So we know it went up 1.5, we can see that. But where else did it go? How far over? Do we know where that asymptote is? So guys, this one's at 0, and this point is at 5. The asymptote is always going to be halfway in between. Okay? Your midline is always halfway in between, like your max and min. So what's halfway between 0 and 5? Yeah, 2.5 or 5 halves again. Yep. And we're shifting to the right, so what do we actually want to say? Minus. Whoops, we don't need more smiley faces everywhere. So that is another way you could do it. If you didn't see it flipped, that's also fine. You could do positive 2.5. And then you just went the other direction. You went to the left. You could have shifted like 7.5 and you'd also be right. So there's lots of ways to get there. Questions, guys? Anything? Yeah. No, because here, let me draw it for you and show you. Because normal sine would do, let me draw it on a different, on a different scale just so you can see it. Normal sine does this, right? So back here, if I did that, and I went to, I can only go to here. Like, if I then shift it, you know, up and to, let's see, which way did we go on that one? To the right. Do you see how it's not going to match up? Like, that should be down here. But if I flip it, it'll let me flip. And go negative. Do you see how now it matches up? Okay. It's poorly drawn, but you see it? Okay. Other questions there? Okay. All right, we are going to jump into notes then. I actually have a worksheet for you today because a bunch of word problems. I don't want you to write those down. So we are starting on this lovely Ferris wheel problem. Okay. Sinusoidal. Yes, it varies sinusoidally. That's just a fun word to say in the morning. So you're riding a Ferris wheel. Hopefully everyone's ridden a Ferris wheel. Yeah, maybe. Otherwise we need a field trip. So this is where you're starting. This is the little bucket you are in to begin with. It says it takes you 7 seconds to get to the highest point on the Ferris wheel, so up here. And when you're up there, you're 55 feet above the ground. We know it also takes 22 seconds for one full revolution of the Ferris wheel. And the diameter of the Ferris wheel is 50 feet, and we are assuming it rotates counterclockwise. It does matter because 7 seconds to get to the top this way is very different from 7 seconds to get to the top going the other way, right? Okay, so that does matter. And your distance varies. Your distance from the ground varies sinusoidally. What that means is as you travel around this circle, your distance away from the ground is not just like a linear path. You're not getting farther away from the ground at the same rate the whole time around the circle, right? Like this is a much steeper change from the ground than like this part is. Does that make sense? That's why like our sine curve, when we unwrapped the unit circle, it's the wave that it is. It's not just linear and straight lines. Okay. So we are going to write an equation to represent height over time with this lovely Ferris wheel. So let's look at all of our pieces here. First, which graph, sine or cosine, is it easiest to see like the maximum height of? Or which one like starts with the maximum height? Cosine, yeah. So we're going to do all of these dealing with a cosine equation, okay? Because we can easily see that maximum height right from the start if we're doing cosine curve, okay? So just a little reminder of your cosine curve. We are talking about the y value being the height in feet, and the x value is your time, and that's in seconds. That's important to note, okay? So one of the first things it says is it takes 7 seconds to get to the highest point on the Ferris wheel. So that means when t equals 0, we are not at the highest point. Okay, when t equals 7, we are at the highest point. So what does that mean for my graph? Like, what sort of shift has happened if it takes 7 seconds to get to the highest point? What do you think? Yeah, horizontal shift. It means the whole thing has moved this way 7 seconds. Okay, so that the maximum happens at 7 seconds. So that's one little piece. We know we have a shift right by 7. Okay, that's one part of our equation. The next part, we're going to talk about the period. How long did they tell us it takes to do one full revolution on this Ferris wheel? 22 seconds. That's the period. Okay, it's how long does it take to go all the way around. So what do I do with that as far as finding something in my equation? What do I set 22 equal to? Yes. And then when I solve for b, what do I have? Pi over 11, right? All right, so that's the next key piece. Okay, now let's figure out what this whole, like, diameter being 50 feet and height 55 feet above the ground, what that has to do with anything. So I'm going to kind of draw on the picture over here. The ground, we'll call that ground. That's going to be at 0 height-wise, okay? Right, makes sense. The ground, you're 0 feet off the ground. It said the Ferris wheel is 5 feet. Well, it didn't specifically say, but do we get that it's 5 feet above the ground? How do I know that it's 5 feet above the ground? Exactly, yeah. We know this whole diameter, which you can't really see the blue in here. We know that's 50 feet, but we also know that up here, the maximum height is 55 feet, okay? The Ferris wheel can't just sit on the ground. That would not go well for anyone. You just have a runaway Ferris wheel. People would get run over. Be no good. So we have this going on. The midline is going to go right through the center of that Ferris wheel. So let's think about a couple of things here. What's the radius of this little Ferris wheel? Yeah, 25 feet. So we know this distance is 25. So where does that put the midline? 30. Okay. All right. So amplitude of this as far as vertical stretch, what is it? Which of those numbers is actually telling me the amplitude? 25. Yes, it's that stretch from the midline to the top. How far that is your amplitude. Okay. And then we have a vertical shift. We've definitely gone up somewhere. How far up have we gone? 30. Okay, a lot of people want to say, oh, it shifted up 5. No, the bottom is 5 feet away from the ground, but remember the vertical shift is the midline. Okay, the middle of your graph tells you what the vertical shift was. So this was a shift up 30. Okay, we've got everything we need to write our equation. So any questions on the 7, pi over 11, 25, or 30? Any of those you're like, I don't know where that number came from. Okay, let's write our equation then. Do you think I need a y equals? Yes, please, when I ask you to write an equation, actually write an equation. All right, amplitude is 25. We said we're doing a cosine equation. B values, pi over 11. In parentheses then, x to the right 7, so minus 7. And then up 30, so outside of all of those parentheses is plus 30. And there is your equation that models this lovely Ferris wheel ride. If you do it one piece at a time, it's not that bad. If you just read the paragraph and think you should just be able to spew out the equation, that doesn't usually go very well. Like, draw things, label stuff on a picture. It definitely helps. Okay? All right, we're actually going to use our calculator for the next part. And guys, I'm going to rewrite this equation in function notation. You don't have to do it this way, but I'm just going to do it with like height and time. So h of t. So we are looking for h of 15 to begin with. So guys, in your calculator, and if you don't have one today, that's okay. Just like try to share with someone. You can use Desmos for now if you want to, but realize, guys, we have to get used to using the TI calculators. There is a calculator portion of the AP exam for you guys, and you can't use Desmos on it. It's all has to be done with your TI. And same thing when you move on to calculus, you can't use Desmos for calculus. You have to use the calculator. So we'll get used to using it, okay? First thing, you want to make sure you're in the right mode. So I'm going to push the mode key. It's in that one of the top rows there. And you can see the third one down. I have radian highlighted. What do you think? Do we want to be in radians or degrees? Radian, yes. Do you know why? Or was it just a good guess? Yeah, in our equation, we put like a pi over 11 as our v value, right? Okay. That's telling us we're talking about radians for this equation. If I'd had something related to degrees in there, then you'd switch to degrees. But for right now, we're going to be in radians, okay? And then once you're in radians, you just get to key this in. So 25 cosine. My fraction shortcut key is not working on this one up here. But if you want to use it, it is the alpha key over here and then the y equals key. And you'll see the little fraction thing come up. Again, mine will not cooperate, so I get extra parentheses. You can type in 15 minus 7. I'm just going to say I know that's 8. And then plus 30. Let's see if we're getting here. If you're not getting this decimal, let me know. Yesterday I had someone who just, everything they typed, they got error on their calculator, so it happens sometimes. Some days you just don't get along with your calculator. Guys, pi is over on the right side if you need it in blue. Guys, once you get that, you can start typing in the other ones too for 30 seconds and 2 minutes. We will eventually. That's ridiculous. But are you okay doing? Just step back. And guys, we are going to round to 3 decimal places. I don't know if I said that. Please put feet after them. So for 2 minutes, what do I put in for the time or the x value? Do I put a 2? No. 120, yeah. Minute of like, how many seconds? So guys, I'll write the others up here. You can check when you're ready. It's going to have an application on it, but not an actual, like you need probably just to write the equation, not actually use your calculator to plug it in. We'll get to some that have full like calculator sections on them, but this one we were like, oh, for like one question, do we want to deal with the calculator? So it'll probably just be the setup. Okay. All right, everybody okay with part B? So guys, part C, what's your initial height just as the Ferris wheel starts turning? Well, what x value or t value am I going to plug in right when it starts? 0, right? Okay, so just find h of 0 for me. All right, guys, what do we get for the initial height? Don't be shy, guys. What do we get? Again, what did you get? Yes, 19.615. Okay, letter D then. How much time has gone by when you first reach a height of 45 feet? So don't write this part down, guys. You could write, okay, the height is 45 equals 25 cosine pi over 11 t minus 7 plus 30, and then algebraically solve for t. Does that look very pleasant to solve for? No, and you guys, there's stuff in there that you'd need to solve it that you don't actually know yet. So I would not ask you to solve that algebraically at this point. What we can do is plug this in our calculator, and I'll go back to X and Y here. Plug this in for your first equation, and then for your second equation, plug in the height of 45 feet, and then we can calculate when these two intersect. We are going to mess with the window, so I'll just give you a minute to type it in, and then we'll do the window part together. Okay, for the window, do you guys see the little key that says window in the very top row? We're going to push that. Maybe. All right, yours will say -10 to 10 probably, and then -10 to 10. Is that what yours looks like? Okay, we're going to adjust that so that we can see everything that's happening. So x minimum of -10 is fine. X max, we're talking about the time here. We know it takes 22 seconds to do like a full revolution. So I'm going to put in maybe 25 seconds for my X max, just so I can see for sure one full cycle of the graph. And then for the Y min, again, -10 is fine. How high up does this Ferris wheel go? Like, what's the maximum height? 55. So I'm going to put in, say, 60, because I don't want the graph just like running into the top of the screen. So I'll change that to 60. And then I'm going to hit graph. Hopefully yours looks something like that. Okay, this is where errors definitely tend to happen. So if you're getting like syntax error or dimension error or anything, if your calculator's not looking like this, let me know and I'll come try to help you. Anybody troubles? No troubles? We had so many troubles yesterday, so you guys are good. Okay. All right, the question says, at what time do you first reach a height of 45 seconds? So that is talking about this intersection right there. Okay, that's the first time you hit 45 feet. The second intersection, that's like you've gone past the top of the Ferris wheel and you're now coming down and you hit 45 feet again, okay? Anybody remember how to actually calculate an intersection with your calculator? Anybody remember where that is? Yeah.
So second trace.
Yep, second trace, which takes you into that calc menu. So trace is at the top, guys. And I did not push second and trace. Okay. Yep, you guys see it? We want to calculate the intersect.
And then the cursor.
Yeah, exactly. You want your little flashy cursor guy to be closer to the intersection you're looking for. It does not need to be right on it, but I want to make sure it's a little bit closer to the one I'm looking for. So I moved it over. And then you'll see at the bottom it says first curve with a question mark. It's asking you, is this the first curve? You're going to push enter. Then it moved and it jumped down. You can almost see it to the other line. It's asking, is this the second curve? The reason it asks this is maybe you have 5 different lines graphed. It needs to make sure, like, oh, am I calculating the intersection of the 2 lines you actually want? We only have 2 lines, but still. And then guess with a question mark. Yes, you want your calculator to guess for you. So push enter one more time, and it will find that intersection. So the time is 3.753 seconds. Okay. Let's jump that one down. All right, then letter E, how much time has gone by when you reach a height of 45 feet for the second time? So that means you need to find the intersection here. So go ahead and try, see if you guys can get the right intersection. I'll put it up here too, just so you can see it. All right, so we got 10.247, it looks like. All right, again, anybody troubles? Okay.
Well, like a few, like just was like 1,000, so like 2.466.
All right, guys, let's try again. All right, water wheeling and dealing. So just like we did for the Ferris wheel and we wrote the equation at the beginning, I want you guys to try to do that for this water wheel. It tells us it rotates 6 revolutions per minute. It takes 2 seconds for this point P over here to get to the maximum height. It looks like your radius of your circle is 7 feet. And then the distance straight down to the water is only 6 feet because that last foot of the wheel was underwater. The water level, that's like a height of 0, okay? All right, so I'll give you a minute here, just like we did with the Ferris wheel. Any sort of shift, what's the period, amplitude, vertical shift, all that stuff, okay? Check in with someone around you guys. Talk to someone. You okay, Kate? Did you stay healthy over break?
I did.
Good job. And did you get caught up on all your stuff?
Yes.
Oh, even better. But now do you feel like you need a break? Yeah. Winter break's coming. Got it? Right.
I think we're saying that the water is 0.
Yes.
So it's still up, and it's going to appear in seconds.
She's saying good things back there. Guys, the vertical stretch out in front, is it a 6 or a 7? It is a 7, yes. Because it's this distance from the top to the midline, or the radius of your circle, okay? Are we ready to go through the whole equation? Okay, so did we all go cosine? Yes, it's much easier. You could write it as a sine, but it's way more complicated, so don't do that. All right, b value, what did we get? Pi over 5. Yes, it said that this can complete 6 revolutions in a minute. So that means it takes 10 seconds for 1 revolution. And then you're just setting that 10 equal to 2 pi over b, same thing we've been doing. Okay, x and then our phase shift. What do we think? -2, yeah, because they told us it takes 2 seconds to get to the maximum height. The maximum height is what you're looking for that sideways shift with a cosine graph. Vertical shift, how far up or down did it go? I heard a whisper of +6. That is correct. Okay, look for the midline right through the center of that wheel. It is up 6. Okay. Questions? Yeah.
So can you just do sine without the minus? Like, you share the same thing?
No, because sine would have to start at the midline. So point P over here would have to be on the midline for it to be a sine graph. And it's not. Do we know how far away it is from the midline? No, it'd be a lot of effort to figure out how to write this as a sine curve. Since they tell us about the maximum height, we want to go ahead and do it as a cosine. Yeah.
It takes 7 seconds to reach the high speed, but it doesn't tell you where to start. Like, does where to start matter?
So they told you start over here. Doesn't really matter. Because if you were graphing this one, you'd be like, okay, 7 seconds, I'm at the maximum height. Like, where it started, we calculated that later to be like 19 feet or something. It doesn't really matter. What matters is like this thing, you know, that you have that curve. And it's just the cosine curve shifted over 7. Wherever the first maximum is, that's the shift for your cosine. Right, because cosine, let's do a new one. Cosine should look like that, right? For the one we just did, so this gets shifted over 2 seconds, right? I don't know, so P is there. If once you write the equation, it's whatever height you get when you plug in a 0 for time. Does that help? Okay. All right, let's try to do B, C, and D. So C and D, you're going to figure out what the initial height was of point B. Okay. All right, guys, so plug those in. So letter B, that's just plugging in x is 5.5. Guys, I'm going to start jotting some answers here. Check when you're ready. Letter C, when does P first touch the surface of the water? You're going to graph that one and look for when y equals 0. So you can graph 2 lines and look for the intersection. You could also just calculate the x-intercept from your graph. And look up here and check when you're ready, and if you're having issues with any of these, let me know.
let's say that. Okay. Okay.
Okay, one more to get through here, guys. And we're going to do this one together because it is slightly different. All right, we're talking about the tide in this problem. So we're on a beach at 2 in the afternoon on March 19th. That doesn't sound like the warmest day to be at the beach, but I guess in Texas, maybe it's not too bad. The water is the deepest when the tide is in, so we measure it to be 1.5 meters deep. And then 8 p.m., we've spent the whole day at the beach, guys. Now we're measuring the water again. When the tide is out, it is 1.1 meters deep. The depth varies sinusoidally again with time. So we need to write an equation, and we're going to base it on a time starting at noon. So let's make a sketch and see what we can come up with here. So I know the maximum height that this water, or the depth of this water, is 1.5, right? That's the deepest it gets, 1.5 meters. And the shallowest it gets in our little area is 1.1 meters. Okay. My y-axis here, I'm going to say that's noon. Okay, 12 o'clock p.m., because that's when they said to start our equation from. We know at 2 p.m. this day, that's when it's at its maximum height. So I'm just going to make a little tick mark here for 2 o'clock. And put a dot up here at 1.5 meters. And then the other thing we know is that at 8 p.m. on that same day, the tide is out, and that's when it's 1.1 meters. So I'm going to leave a little space here, put a tick mark, and say 8 p.m. And that's when I get a dot at 1.1. Okay. Lovely. Lots of information here. So let's think about a few things. 1.5 is the max, 1.1 is the minimum. Where's that midline going to be? 1.3, okay. All right, and it hits the maximum at 2 p.m. and the minimum at 8 p.m. How many hours is it from 2 to 8 p.m.? 6. So it's going to hit the midline halfway in between. What time would that be? 5. We don't really need that, but I think it helps with the picture. All right, so what I know so far is this much of the graph. How much of the cosine graph did we see in that little 6-hour window? Half of it, right? Okay. So it took 6 hours to see half of it. What does that make the period? 12 hours, yes, okay. So we'll do our normal, 2 pi over b equals 12. What do we get for our b value? Pi over 6. All right, so there's one piece. And the other pieces are a little bit easier to find. What is the amplitude of this one? 0.2. Yeah, kind of weird, but yes, it is 0.2. Vertical shift, how far up did we go? 1.3. That's why we find that midline, guys, because that's your vertical shift. And what about the horizontal shift? We definitely went over to the right again. How far? 2. Yeah, from noon to 2 p.m. is 2 hours, so that's a shift right of 2. It's kind of weird when your x-axis is in time, like literally times, not just seconds or hours or minutes or something. But we do shift over 2 hours to the right. So let's write that equation. Y equals amplitude of 0.2, again, cosine pi over 6, x minus 2, plus 1.3. Is it getting a little easier? Like dissecting the word problems, we can find the pieces we need. Again, the picture, like draw things. Do not be afraid to draw pictures with these. It's very helpful. I need that to help me visualize what's happening. All right, so let's answer. Guys, I want you to try B and C for me, but you can skip letter D. Let's just do these last two as we are running out of time. So use that equation. Use the equation or just extend your graph here and think about where these things would be happening, okay? This is why I said skip them, and I used to have it, like, did you do it?
I rounded it to like the whole number because I didn't feel like doing it.
Oh, okay. So then maybe did you do 5 then? Although that would have been 5 a.m. instead.
Or like I ended up with
This one's
my graph was at 16 and 23, so then I just added that to 12 and then subtracted 24 minutes to 5.
Okay. Let's see why I just
Yeah.
yeah. Okay. It's a little.
Yeah. I was like, I was
little
solving it and I was
quirky.
like, I don't like this.
Yeah. Exactly.
I have one piece of mind. When we're gonna do the test, you're not gonna make us like find the amount of time that the wheel is like underwater or anything. Right?
It's not gonna be anything crazy. It's gonna be like this part
My
of
math
it.
teacher last year, he made us like find like percentages and stuff like that for those problems, and that's why like the word like Ferris wheel or like just a wheel problem just gives me like
Gives you a side.
it's like
No, it's
if
literally
I have to
gonna be
like
something.
find like signs and percentages and then multiply it by everything, I'm done. I'm out. I'll go back to algebra 2.
Yeah. No, it's just gonna be like taking this and getting right here.
Okay.
Because you're not going to calculate it. So it's gonna
Oh,
just
we're
be.
not. Oh, so it's just.
It's like having to deal with making a calculator part.
Yeah. Yeah, that makes sense.
Yep.
Okay. Great.
You'll be just fine. So guys, you can certainly do a lot of this, like you can plug it in and use your calculator and all of that. But with the period being 12 hours and this being like time related, it's actually pretty simple. So use your equation to predict the depth of water at 5 p.m. on March 20th. What is the depth at 5 p.m. always? What was the depth at 5 p.m. when we sketched it? 1.3. And then 5 a.m. it's going to be 1.3, and 5 p.m. it's going to be 1.3 because it's going to follow every 12 hours. It's going to repeat. So that one should be 1.3 meters. And then following that same logic, what's the date and time of the second low tide afternoon on March 19th? So this 8 p.m., should put a p.m. by it, was the first low tide. So when is the next low tide going to happen? 8 a.m. on the next day, right? 12 hours later. With the period being 12 hours, that really simplifies things. So 8 a.m. on March 20th. Okay? You can use your calculator, but, you know, you can also just think through these 12-hour time windows. All right, guys, the math space is posted for you. It's only 4 questions, but they are for, like, part A, B, C, D, like they're multi-part questions. So that's up. On Thursday, we will review. So a whole day of reviewing Skill 5, and then next week on Monday is your actual assessment, okay? And it's almost December 7th.